We are live at the 2026 SPWLA Annual Symposium, the 67th Annual Symposium. My son would say 6-7, 6-7. But we are in the poster sessions. The poster sessions, it's different. It's not like the technical talks. You're not sitting and listening to it all, and then you have a question at the end. Poster sessions allow you to ask, to learn the information and understand the data just the same, like in real time, but you can stop and ask a question to the presenter. That's what, it's unique, it's different, and we wanted to take the time to do a mini podcast with one of the presenters. Please introduce yourself and tell us about salts and dielectric measurements.
Yes. Hello everyone, my name is Mariella Khoury. I'm a PhD student at the University of Texas at Austin. And my poster today is about the influence of brine composition, including salt concentration and type, on dielectric permittivity. So I will go real quick on this. So previously, people have shown that dielectric permittivity strongly depends on the salt concentration in brine. However, they focus on salt concentration, and they assume that the salt type is NaCl. But like, what happens if we have other salt types, let's say KCl? And what happens if we have some mixtures of salts? For example, people are now looking into lithium in brine. So to see that, first we look at dispersion curves, the same rock at different salt concentration and types, and we see that the dispersion curves do depend on the salt concentration and type. Now this becomes important during the interpretation. We can see that the water-filled porosity depends on salt concentration and type both. Well, these results are for one rock. But what happens if we have different rocks, different pore structures? What is the combined impact of brine composition and pore structure? So we have wireline dielectric tool. It operates between 20 megahertz and 1 gigahertz. And in this frequency range, we have two overlapping polarization mechanisms: Maxwell-Wagner polarization and orientational polarization. Well, they told me I only have 5 minutes, so I'm not going to details, but you can ask. So Maxwell-Wagner depends on the brine conductivity and the pore structure, while orientational polarization depends on both brine conductivity and brine relative permittivity. So there's one technique that people use to isolate the impact of brine conductivity, where they divide the frequency by brine conductivity. And if you do that, the changes in relative permittivity can be attributed to brine dielectric properties. Please focus on this because I will show results related to this part. So, yeah.
The recap I'm trying to capture in my mind while you're talking, because we're talking about the electrical current through the media that's a salty brine and how it changes the conductivity, the speed at which electricity can travel through, and you're able to manipulate the concentrations of salts and to make it mimic, even though they're different and in different porosities, they'll do the same thing from a dielectric.
So we have, as I mentioned here, we have two overlapping mechanisms: Maxwell-Wagner polarization and orientational polarization. To kind of understand how this normalization over brine conductivity works, we have to understand how brine conductivity affects these properties. How does brine conductivity affect these properties? It changes their relaxation. So instead of this relaxing earlier, now it will relax after. But what happens if you divide frequency by brine conductivity? Now the impact that brine conductivity has on the relaxation related to frequency will be normalized. So all these curves will overlap. There will be some differences. And if there are these differences, this is due to the different salt type, not related to the conductivity. Because complex relative permittivity is two parts: conductivity and real relative permittivity. So if you remove the impact of brine conductivity, you'll see the impact of relative permittivity.
Can you define relative permittivity?
Yeah. So relative permittivity is, first of all, it's relative to the relative permittivity of vacuum, first of all. Second of all, this is a property that quantifies how much this rock can store energy.
Whoa.
Yeah.
That's permittivity. Okay.
Yes. So to do this, we perform a frequency domain simulations. And the inputs to this simulation are, first of all, 3D micro CT scan images, and we use images with different pore structures, as well as the brine dielectric properties of the brine inside these rocks. We get these properties using dielectric measurements, using coaxial probe and network analyzer at ambient temperature and pressure. We consider NaCl, KCl, and CaCl2, including their mixture between 10 to 200 kppm. Yes. So now I will introduce the rock samples. So I simulate 3 rock samples: Berea sandstone, Austin chalk, and Happy Spraberry. As you can see here, these are the micro CT scan of these rocks, and we get the representative elementary volume to kind of have a similar porosity, so that we don't have to worry too much about the impact of porosity. And we compute Archie's M exponent just to get an idea about how much are the pore structure different. And what we can see is that, yes, they are different. Yeah, exactly. Visuals and even quantification. Now moving on to the results. These are the dispersion curves of these different rocks. And looking at 100 kppm, between 20 megahertz and 1 gigahertz, relative permittivity decreases by 38% for Berea sandstone, 101% for Austin chalk, and 192% for Happy Spraberry. And this is showing how significant pore structure affects the dispersion of relative permittivity. Yeah, yes. Because this polarization mechanism, you apply an electric field and you have ions, right? So these ions will try to follow this electric field. But when you have complex pore structure, some of them cannot reach there, so they get accumulated on the surface of the rock, and this causes an increase in energy storage. So when you have more complex rocks, what we see is that now the storage is increasing compared to Berea sandstone, which has relatively more homogeneous pore structure compared to these other rocks. And what's interesting here is that if you look at the M exponent, you have 1.95, 2.29, and 2.57, which kind of gives you also the trend of how the dispersion is behaving. Now we apply this that I explained before, normalization for brine impacts. And what we see is that the relative permittivity decreases with brine conductivity. But what's interesting is that at low brine conductivity, relative permittivity is not so sensitive to salt type. However, as brine conductivity starts increasing, now we have more impact to the salt type. Okay, this is nice, but why do we care about this, right? What are the impacts? What are the implications on interpretation? So for us to understand this, we compute the error in CRIM-based water-filled porosity, assuming constant brine permittivity. What we see is that, well, this assumption works relatively well for Berea sandstone at low salt concentration. But as salt concentration increases, now the error increases. And if you look at Austin chalk and Happy Spraberry, now the errors are amplified. In fact, for KCl, it can reach up to 60%. Furthermore, the relative error is also dependent on salt type. In conclusion, dielectric dispersion, as we've seen here, strongly depends on pore structure. Salt type have measurable impact above 15 Siemens per meter. And assuming constant brine permittivity can lead to up to 60% error in water-filled porosity for these rocks. And finally, the reliable interpretation of dielectric measurements requires taking into account salt type, salt concentration, and pore structure. I want to conclude this by acknowledging our sponsors, and we appreciate them for supporting our research. Thank you. Thank you for coming by.
Dang. Picture?
Thank you so much.
Yeah, I'm still, okay, I'm not going to act like I don't quite understand relative permittivity as far as like it's an energy thing.
Yes.
But am I following enough that if you're collecting the dielectric measurements of the reservoir, that maybe you can start to adjust the chemistry of your frac fluid that you're going to break this rock with?
Well, to break your rock, you have to look at the mechanical properties, but
to fill the crack that you're going to break the rock with something that's going to interact with the rock surface. You don't want to put something in there that doesn't want to react with the rock. You want reaction with the rock because that's where the kerogen's at, that's where the oil's piling up, right? Is that kind of what you're thinking with?
not quite, because to do this, we need to look at maybe more at the geochemistry, how the different brines interact with the rock. But here what I want to say is that people are using these measurements when we use them. Where should we take into account salt type? At which conditions? And here you can see that salt type for Berea sandstone, a homogeneous rock, it's okay, you don't have to take into account salt type. But for more complex, now this becomes more important. And this is also showing that the relative permittivity is sensitive to salt type, which means you can also get valuable information about the salt type if you are interested. To know more about your salt type, you might be able to use these measurements.
So there's, in your opinion, there's like three kind of different salty brines. You got KCl, NaCl, CaCl too.
And mixtures.
And mixtures. You can have a combination of those, but there's really no other anion-cation mixture that's going to make a salty brine.
There is, but we use these because when we looked at some data published, we see that the formation waters that are present usually contain the most these salt. So this, yeah, exactly, most abundant salts. This is why we looked at these, but there are many others, but they're not as abundant, maybe more traces, and maybe people won't care so much about taking them into account, because if you have like really small concentration of this, it might have no impact at all.
Dilution kind of factor. Okay. Well, very cool. Thank you.